Ever hit send on an email or, stream a movie, maybe just log into your work account. And you just wonder what incredible digital gymnastics are happening behind the scenes to make it all work, or maybe how massive companies manage all their digital magic and it seems so effortless. It's really like looking under the hood of the entire modern world. And once you start to see what's actually under there, well, it's absolutely fascinating. Today, we're taking a deep dive into that very world. It's the often hidden but absolutely critical realm of IT infrastructure and the revolutionary impact that cloud computing has had on it. We've got a stack of incredibly insightful sources here to guide us, really full of surprising facts, clear explanations. It'll give you a shortcut to being pretty well informed on this.
That's right. Yeah, our mission today is basically to unpack the core components of this digital backbone. We want to demystify all the jargon you might hear and really reveal how organizations are building, securing, and constantly optimizing their digital foundations. We'll explore everything from the physical wires and machines they own themselves, like in their own buildings, to the vast sort of invisible resources they rent from the cloud. You, our listener, you'll walk away with a much clearer understanding, hopefully crystal clear, of what truly powers our connected world.
Okay, let's unpack this right from the beginning then. When we talk about IT infrastructure, what exactly are we talking about? It sounds incredibly broad. Like it could be anything from a tiny chip to a massive data center.
It definitely is broad, yeah, but it's also got a pretty precise definition. And getting this right is fundamental to understanding how modern businesses actually operate. Think of IT infrastructure as the foundational supporting IT architecture. You find it within pretty much most modern companies. It's composed of multiple interconnected technological components. And crucially, this core infrastructure involves a combination of both on-premises stuff.
On-premises meaning like physically there in the company building.
Exactly. Physical hardware located right there in companies' own facilities, and then also outsourced hardware, software, and very importantly, the specialized people, the personnel who manage it all. It's not just the tech itself. It's the people and the process that bring it all to life.
Okay. So it's definitely not just the computers we see on our desks then. It sounds like many organizations aren't even owning all that hardware anymore. That feels like a huge shift from how things maybe used to be.
It's exactly right. While those end-user devices, your laptop or desktop, are part of it. The larger trend, definitely, is that many organizations are increasingly relying on third-party providers to support their IT operations. They're realizing that managing every single piece of hardware, every software update internally, well, it can be incredibly resource-intensive, and often it just doesn't align with their core business focus. This shift, in turn, has caused this really aggressive growth in the focus on quality system and organization controls, or SOC2 engagements. You hear that term a lot now.
SOC2, right.
It's become absolutely vital to have that external validation because, if you're outsourcing something so critical, you need assurance it's being handled securely, reliably.
So that's where SOC2 engagements come in. Okay. We hear about them a lot, usually in the context of data security, compliance maybe. But what exactly are they, and why are they so incredibly important when a company starts outsourcing its IT? It sounds like more than just a simple audit checklist.
Great question. And they are indeed critical. What many people don't maybe realize about SOC2 is that it's not just a checkbox for compliance. Not at all. It's actually a critical mechanism for building trust in the digital economy, which is kind of revolutionary, given how much sensitive data is now managed by third parties.
Trust. Okay. That makes sense.
So to define it a bit more formally, SOC2 engagements are examinations. An independent third party comes in, evaluates, and then reports on a service organization's system controls. And this evaluation is based on a very specific set of criteria, developed by the American Institute of Certified Public Accountants, the AICPA. These are known as the 5 Trust Services criteria: security, availability, processing integrity, confidentiality, and privacy.
Security, availability, processing integrity, confidentiality, privacy.
Right. And the core purpose of these reports, it's to give the users of that service organization's systems, often their clients, to give them reasonable assurance that the controls, as described in the system documentation, are 1, accurately depicted, and 2, perhaps most importantly, that they are effective in practice.
So it's not just what they say they do, but that it actually works.
Precisely. While SOC2 audits can involve really any third-party company that manages or has access to sensitive data, they typically focus on companies whose primary business is managing the IT function for other organizations, the CSPs, the managed service providers, And for the auditors themselves, conducting these engagements really emphasizes that they need more than just basic IT knowledge. They need an advanced understanding of IT terminology, yes, but also deep technical expertise. Expertise in how the key components of the modern IT landscape actually function.
Like what sort of component?
Well, things like operating systems, network infrastructure topologies, we'll get into that, end user devices, and all the hardware used across these domains. It really speaks to the complexity and specialization required today. You can't just wing it.
That makes perfect sense. Auditors can't just check boxes. They need to truly understand the nuts and bolts of the systems to provide that independent assurance, that trustworthiness. So let's get down to those nuts and bolts then. Hardware. When we think about an organization's IT infrastructure, what are the key pieces of computer hardware involved? I'm curious about the distinction maybe between what we use every day and what makes the whole system run behind the scenes.
Right. So at its most basic level, computer hardware refers to the physical components.
Yeah.
The actual tangible machines and devices. This includes computers themselves, the internal physical components that make up those computers, computer-related equipment, and external peripheral devices. Keyboards, monitors, that sort of thing. When we think about how these are used in an organization, we can broadly categorize them into a couple of groups based on who primarily interacts with them. First, we have what are called end-user devices, or EUDs. These are the electronic machines, typically computers or maybe mini-computers, that directly interact with employees or consumers, right at the edge of a network.
The edge, like where people actually touch the system.
Exactly. Think of them as the human interface. The point in an organization's IT architecture where a human directly interacts with the system. So examples are, company-issued laptops, desktops, tablets, maybe even wearables now. An important distinction here is that EUDs are used by someone who is strictly the final consumer of that device. For their day-to-day tasks, they are not used by, say, programmers, administrators, or developers, the people responsible for building, maintaining, and repairing the underlying infrastructure.
Ah, okay, so my work laptop is an EUD, but the powerful server sitting in some data center somewhere, that makes a lot of sense.
Exactly. Those intermediary individuals, the IT professionals, they work with what we call non-EUDs. These are devices like switches, servers, routers, and other network support devices. They underpin the entire system, working behind the scenes to keep everything running smoothly.
Got it. Non-EUDs are for the IT folks managing things.
Yes, precisely. Then we have the internal computer hardware. These are the essential components found inside a computer, making it function. This includes the microprocessor, often called the brain of the computer, right? Performing all the computations.
The processor, yeah.
You also have graphics and sound cards for visual and audio output, hard drives for permanent storage, all your files, your programs, and random access memory, or RAM. That's for temporary high-speed storage the computer uses while it's actively working on tasks.
Like short-term memory.
Kind of, yeah. Very fast short-term memory. The power supply, obviously, provides electricity to all these components, and the motherboard acts as the central hub. It connects almost all critical pieces together, allowing them to communicate with each other.
Okay, so that's the inside stuff. What about outside?
Right, beyond the internal components, there's external computer hardware, or peripherals. These are devices that connect externally to a computer, either wirelessly or, through a wired connection. Think of common items like computer mice, keyboards, speakers, microphones, monitors.
This stuff we plug in.
Pretty much. But it also extends to other devices crucial for an organization. Things like disk drives, external memory devices, network cards, printers, scanners. Even some networking equipment can fall into this category, depending on how it connects.
It's easy to just think about the devices themselves, the laptops and servers, but these physical components have to live somewhere, right? What about the actual physical spaces that hold all this crucial hardware? Are they just big rooms full of racks, or is there more to it?
That's a vital point.
Yeah.
And yeah, often overlooked when people think about IT. While not hardware themselves, the facilities and the safeguards on those facilities that contain hardware, places like data centers or server rooms and offices, they are absolutely a crucial part of the broader IT infrastructure. Their importance really can't be overstated.
Imagine a massive, complex brain. It needs a stall, right, to protect it.
Good analogy.
These spaces require advanced security systems to monitor and control access, ensuring only authorized personnel can get near the sensitive equipment. We're talking biometrics sometimes, multi-factor authentication, constant video surveillance. Often they're like fortresses.
Wow.
But it's not just about security from people. It's also about environmental control. These facilities need robust ventilation and climate control systems to keep temperatures down, prevent the equipment from overheating.
Because they generate a lot of heat, right? Those
Huh.
processors working. A huge amount of heat. A server that overheats is basically a server that's not working. And that can bring down critical operations instantly. And when you think about the sheer amount of power these servers draw and the heat they generate, well, maintaining that optimal environment becomes a monumental task. It consumes significant energy and requires dedicated infrastructure
Yeah.
just for the cooling and power. It's a continuous, often hidden operational expense.
Okay, here's where it gets really interesting for me. We've got all these individual devices, EUDs, non-EUDs, sitting in their climate-controlled fortresses. But how do they actually talk to each other? How does information flow from my laptop to a server, or from one department's computer to another's? Imagine a world where every computer was just an island. That's essentially what we had way back, before networks. So how did we build the bridges that connect all our digital islands? That's where networks come in, right?
Absolutely, you nailed it. Networks are the circulatory system of IT infrastructure. They make those connections possible. Network infrastructure refers to the combination of hardware, software, the physical layout, and the underlying rules or topology of network resources that all work together to enable seamless connectivity and communication between devices on a computer network. It's how everything communicates and shares resources.
Okay, so what are the key pieces, the hardware components of this network infrastructure?
Right, let's break down the key hardware components because each plays a specific and crucial role in building these bridges. First, we have modems. Think of a modem as the internet's front door for your home or office. It's the device that connects your local network to an internet service provider's network, your ISP, typically through a cable, fiber, or maybe DSL connection.
The box the internet company gives you usually.
Often, yes. And what it does is translate the analog signals from your ISP's network into digital signals that your devices can understand, and vice versa. Each modem has a unique public IP address. That's how it's identified and communicates on the vastness of the internet.
Okay, the front door, what's next?
Next are routers. If the modem is the front door, the router is the traffic cop inside your network.
I like that analogy, traffic cop.
Yeah, routers manage network traffic by connecting multiple devices to form a local network. They're smart. They read the source and destination information in data packets, these discrete units of data being communicated,
Right.
to determine the most efficient path for that data to travel through the network. They also act as a crucial link between your modem and the organization's switches, usually. In smaller setups, if there are no switches, the router might connect directly to user devices.
Okay, so modems connect to the internet, routers manage traffic within the network. What about switches?
Right. Then there are switches. These are similar to routers in that they connect and divide devices within a computer network. But they don't perform as many advanced functions, like they don't assign IP addresses or route between different networks. A good analogy is thinking of a traditional power strip for electrical outlets. It converts one electrical outlet into multiple outlets.
Yeah.
A network switch does the same thing for network jacks. It allows multiple devices to share one network connection efficiently, but usually just within the same local network.
Like a multi-outlet adapter for network cables. Got it.
Then we have gateways. These are fascinating. Imagine them as a language translator between different networks.
Translator? How so?
Well, a gateway is a computer or device that acts as an intermediary. It transforms data from one protocol into another, so that information can flow seamlessly between networks that might otherwise speak different digital languages.
And a protocol is just the set of rules for communication.
Exactly. A protocol is simply a set of rules that governs how information is transmitted. A gateway interprets these differing protocols and converts them into the appropriate format to facilitate network movement, usually between a company's internal network and the vast external internet. Without gateways, distinct networks wouldn't be able to talk to each other at all. They'd be incompatible.
Okay, that makes sense. Vital piece.
Definitely. We also have edge-enabled devices. These are increasingly important for modern distributed computing. They allow computing, storage, and networking functions to occur closer to the devices where the data or system request originates, rather than having everything routed way back to a distant central location.
So processing happens nearer to the source.
Exactly. Think of them as mini data centers right at the edge of the network. The benefits of this distributed computing power are significant. Faster network response times, reduced network congestion, and improved operability because data doesn't have to travel so far to a remote centralized server for processing. It brings computation closer to where the action is, critical for things like real-time analytics or, self-driving cars.
Right, where latency matters a lot.
Precisely. And of course, servers. Can't forget servers. These are essentially the central brains or service providers for network devices. Servers can be physical machines or they can be virtual machines now that coordinate the computers, programs, and data within a network. Most business networks operate on a client-server model. A client device, like your laptop, sends a request to the server, and the server provides a response or executes some action. There are various types, specialized for different tasks, like web servers for hosting websites, file servers for storing documents, print servers for managing printers, database servers for handling structured data. Lots of different roles.
The workhorses of the network.
Absolutely. And finally, we have firewalls. These are your crucial security guards at the network's border.
The bouncers.
Yeah, kind of. Firewalls are software applications or hardware devices that protect a network. They do this by filtering network traffic through security protocols with predefined rules. For companies, these rules are often aligned with company policies and access guidelines. Their primary intention is to prevent unauthorized access into the organization and also to prevent employees, maybe from downloading malicious programs or accessing restricted sites.
So how do these firewalls actually work their magic? Are they all the same, or are there different levels of sophistication to these digital security guards?
Oh, not at all the same. They vary quite a bit in sophistication. The most basic are packet filtering firewalls. These work by analyzing network traffic transmitted in packets. They look at simple things like the source or destination IP address and determine if the firewall software is configured to accept that data based on those rules.
So like checking the address label on a package.
Pretty much. If the address isn't on the approved list, it simply blocks the packet. Firewalls can be set to only allow trusted sources to transmit across the network.
But what about more advanced threats? Can they look inside the package?
Exactly. That's where the more advanced types come in, often categorized as next-gen firewalls. These are far more intelligent. They can inspect the actual content of the data. They can understand which applications are being used and even identify specific users who are generating the traffic.
Wow, okay. So much more granular.
Very granular control, yes.
Yeah.
This allows for rules where, say, a low-shred application might have more permissive rules, while a high-security application, or maybe a specific user handling sensitive data, has a highly restrictive rule set applied. The goal is to provide deep inspection and context-aware security, adapting to the dynamic nature of network traffic, not just looking at addresses.
Wow, that's a lot of specialized components and critical security measures. But the actual way these devices are physically arranged, that also matters, right? It's not just about having the right parts, but how they're laid out. Does that layout affect how the network performs, like dramatically?
Absolutely. Massively sometimes. This is where network topology comes into play. Network topology refers to the physical layout of equipment, or nodes, in a network. Understanding this layout is essential for properly engineering the network for optimal performance. Each topology has different requirements for components, like the length and type of connecting cables, the data transmission rates needed, the physical position of each node. These variables are determined by factors like, well, the size of the network, the performance needs of the organization, and the specific environment in which the network is built.
So what are the common ways to arrange them, the common topologies?
There are 4 common types of network topologies that we should probably understand. Each has its own benefits and drawbacks. First, the bus topology. Imagine a single long cable, either linear or maybe in a tree form, and each node is connected directly to that central line.
Like beads on a string.
Kinda, yeah. Data can be transmitted by any node on the system at the same time. The main benefit is simplicity, and it's low cost for small networks. However, a major disadvantage is if that central line, that bus, is compromised or breaks, the entire network goes offline.
Ah, single point of failure.
Exactly, making it less reliable for critical operations. Second, the mesh topology. In this layout, there are numerous connections between nodes. In a full mesh, every single node is connected to every other node. In a partial mesh, only some are connected like that.
That sounds complicated.
It can be. This is commonly used in wireless networks because it's very robust, while the sheer number of pathways allows for high levels of traffic and promotes network stability. Because if one node is damaged, there are many other paths for data to travel. It can be quite costly and complex to implement and maintain over the network's lifespan, just due to all those connections. Think of it as a super redundant web.
Okay. Robust but expensive. What else?
Third, the ring topology. Here, nodes are connected in a circular path, like a ring. When data is transferred to a destination device, it must first pass through every other device between the source and destination on that ring. You can have unidirectional ring paths, where data only moves in one direction, or multi-directional paths, allowing two-way data transmission.
Seems organized, but maybe slow.
You got it.
Weird.
An advantage of ring topologies is that data transmission collision is minimized or even eliminated because data flows in an organized manner. But this can unfortunately result in very slow network performance, especially as the network grows, because data has to pass through so many points.
Right. And the last one.
And fourth, the star topology. This is one of the most common and widely deployed topologies today. You see it everywhere. In a star topology, all data passes through a central hub. This acts as a switch, or maybe a server, and then it transmits to peripheral devices that act as clients.
Like spokes on a wheel connecting to the center?
Perfect analogy.
Yeah.
And the advantage here is that you can have multiple hubs. So if one hub fails, only the nodes connected to that specific hub will stop functioning, not the entire network. Even though the hub itself is a single point of failure for its connected nodes, this structure makes it much easier to identify damaged cables and isolate problems. It simplifies troubleshooting and maintenance a lot.
Okay, so star is common because it balances reliability and manageability.
Largely, yes. It hits a sweet spot for many organizations.
So we've got the physical components, and we've got how they're physically arranged, the topology. But how do they understand each other? I imagine it's not just about plugging things in correctly. Protocols are like the rules, right? The common language they all agree to speak. This feels like where the magic really happens for actual communication.
Exactly. You've hit on a critical point there. Devices in a network communicate with each other using protocols. These are the rules that govern the way data is transmitted. Defining everything from the method used is to a specific type of cable, a specific port, a wireless transmission mechanism.
So the how of sending data.
Right. And the best way to understand how these protocols work and how networking devices communicate is through the Open Systems Interconnection Model, or OSI model. It was developed by the International Organization for Standardization, ISO. And the OSI model conceptually segregates network functions into 7 different layers. Each layer is responsible for a specific data exchange function.
7 layers, wow.
7 layers. And the real aha moment of the OSI model is that it allows different hardware and software from countless manufacturers to all speak the same language. Without it, the internet as we know it just wouldn't exist. It couldn't function.
It standardizes everything.
Exactly. Imagine trying to talk to someone if every single word required a different translation app. That's what we'd have without this layered, standardized approach. Now, data flows through these layers in a process called encapsulation when it's being sent.
Encapsulation, like putting it in capsules.
Kind of.
Yeah.
Think of it like putting a letter into an envelope, then putting that envelope into a larger package, and maybe putting that package in a shipping crate.
Okay, adding layers of packaging.
Precisely. As data moves from the top layer down, each layer adds a header, or maybe a footer, to the data it receives from the previous layer. It's essentially adding its own instructions or identifying information. This process starts at the application layer with a message, which is then passed down to the presentation layer where a header or footer is added, and so on. The data continues this encapsulation process through each layer down to the physical layer, which represents the actual networking device being used to transmit the message. At the physical layer, the message is transformed into electrical impulses or radio waves or light signals that are then sent to the receiving networking device.
So it gets packaged up layer by layer, then sent out physically. What happened on the other end?
On the receiving end, the process is simply reversed. It's called decapsulation, unpacking it. The message starts at the physical layer, gets converted back from bits into something meaningful, and then moves up through each layer. Each layer strips off and interprets the header that was added by its corresponding layer on the sending device.
So it unpacks it layer by layer until you get the original message.
Exactly. It's a highly structured and efficient way for complex data to travel across networks, without any single piece of hardware or software needing to understand the entire journey from start to finish. Each layer just does its specific job.
That sounds incredibly intricate and yet so genius in its design. Can you walk us through those 7 layers, maybe from the top down? Give us a clear picture of what each one does functionally, without getting totally lost in all the specific technical acronyms. I just want to understand the purpose of each step in this digital journey.
Certainly. Yeah, let's start from the top closest to the user and work our way down to the physical transmission. Layer 7, the application layer. This layer is the interface between the user's applications like your web browser or email client and the network protocols needed to transmit a message. It doesn't represent the actual application itself, but rather the services that allow applications to interact with the network.
So it's like the app saying, hey, network, I need to send this email.
Pretty much. Think of it as the network knowing what you want to do, send an email, browse a website, transfer a file. Protocols like HTTP, FTP, SMTP live here.
Okay, the intent layer.
Layer 6, the presentation layer. This layer's job is to transform data received from the application layer into a format that other devices using the OSI model can interpret. Think of it as the translator and formatter for the network.
Making sure everyone understands the format.
Exactly. This is where data is prepared for network transmission, converting it into standard formats for videos, images, web pages, so that different systems can understand each other's data. Encryption and decryption also typically happen at this layer, ensuring your data is secure or made readable. ASCII, JPEG, MPEG formats are relevant here.
Okay, translation and formatting. Next.
Layer 5, the session layer. Layer 5 allows communication sessions or dialogues between communicating devices to be established and maintained. It manages and synchronizes the conversation, determining which side can send data at what time, and ensures that the connection remains open for the duration of the data transfer.
Like managing the phone call itself, setting it up, keeping it going.
Exactly like managing a phone call. Setting it up, keeping it active, and tearing it down gracefully when done. Protocols like RPC, SQL, NFS operate here.
Okay, layer 4.
Layer 4, the transport layer. This is a really crucial layer. It supports and controls the communication connections between devices. It's responsible for segmenting data into smaller packets for efficient transmission and then reassembling them at the receiving end.
Breaking it down and putting it back together.
Right. And this involves setting rules for how devices are referenced, determining the amount of data that can be transmitted, validating the data's integrity, and handling error recovery, like determining whether data has been lost and retransmitting it if necessary.
So if my video call gets pixelated, this layer might be trying to fix it.
It's very likely working overtime to try and resend missing pieces of data, yes.
Oh.
TCP and UDP are key protocols here, along with SSL TLS for secure transport.
Crucial. Okay, layer 3.
Layer 3, the network layer. The network layer is all about routing and logical addressing. It adds logical address headers to the data, such as the source and destination IP addresses. That's how the message reaches the correct devices across different networks, potentially globally.
The global address system, IP addresses?
Correct. It's responsible for finding the best path for data to travel from one point to another, much like a GPS system for data packets. IPsec NAB protocols are active here.
Okay, the routing layer. 2 more to go.
Layer 2, the data link layer. In the data link layer, data packets are formatted for transmission across a specific physical link, like an Ethernet cable or a Wi-Fi signal. This layer determines how data is physically sent and received based on the specific hardware and networking technology being used right there. It also adds unique hardware identifiers, often called MSE addresses.
MSE addresses. I've heard of those. Different from IP addresses.
Yes, very different. MSE addresses are permanent hardware identifiers, like a serial number for your network card. They act as source and destination reference numbers to route messages to the correct device within a local network segment. IP addresses handle routing between networks.
Ah, local delivery versus global delivery.
Good way to put it. Ethernet is a common Layer 2 technology. Protocols like ARP-Link IP to MC addresses.
Okay, final layer, physical.
And finally, Layer 1, the physical layer. This is the lowest layer and deals with the actual physical medium and the electrical optical signals. It converts the message sent from the data link layer into bits, the literal ones and zeros, and transmits them via physical devices, as electrical impulses over copper wire, light pulses over fiber optic cable, or radio waves for wireless. Conversely, it receives messages from other physical devices and converts those bits back into a format that can be interpreted by the data link layer.
This is where the bits literally move, making the actual connection.
Exactly. It's all about the physics of transmitting signals.
Mm-hmm.
Cables, connectors, voltage levels, frequencies, that's Layer 1. HSSI, SONET are examples here.
That's a lot of layers. It really illustrates how much goes into just a simple click or data transfer, and how each step has such a specific job. It's amazing it works so seamlessly most of the time. So with all these layers and specialized hardware, what does this all mean for how an organization designs its whole network? You know, the big picture architecture. How do they pull all this together to make it work for their specific needs? Is it just throwing components together?
Definitely not just throwing components together. The network infrastructure architecture refers to the holistic design structure of a network. It's the blueprint. It considers factors such as geographical layout, the physical and logical arrangement of components we've discussed, and the network protocols used. It's about crafting a comprehensive plan that aligns with the organization's goals, whether that's supporting a small office or a massive global enterprise. Networks can be wired, wireless, virtual, or on-premises. They can utilize a variety of hardware and software to enable connectivity, and they can be spread across a wide geographical area or confined to a more narrow, concentrated one.
So what are the common types of these big picture designs?
There are several common types of network architecture designs. We have local area networks, or LANs. These provide network access to a limited geographic area, like a home, a single office building, or maybe a university campus. They are typically owned and managed by a single organization and usually offer high-speed connectivity within that limited space.
My home Wi-Fi is basically a LAN.
Exactly. Then there are wide area networks, or WANs. These provide access to much larger geographic areas, cities, regions, even entire countries. WANs connect other networks together, like linking multiple LANs from different company branches to provide broad coverage. The largest and most familiar example of a WAN is, of course, the Internet itself, connecting countless networks worldwide.
Connecting all the LANs and other WANs together.
Right. Now, an interesting evolution is the Software-Defined Wide Area Network, or SD-WAN. In a traditional WAN, the control and management of the network are often integrated directly into the specialized hardware routers. With an SD-WAN setup, the control and management functions are separated from the hardware and moved into software, centralized software control.
What's the advantage of that?
Greater flexibility, centralized control, and dynamic optimization. An SD-WAN actively monitors the performance of the different WAN connections available. Maybe you have broadband and cellular backup. And it intelligently manages traffic to optimize connectivity dynamically, ensuring critical applications get the bandwidth they need, maybe routing less important traffic over a cheaper link or routing around congestion automatically. It's a much more agile way to manage complex wide area networks.
Very smart.
Okay, what else?
Finally, we have virtual private networks, or VPNs. These are virtual connections that provide remote and secure access to an existing private network, usually through a secure channel or tunnel over a public network like the internet.
VPNs. Lots of people use those now for work, right? Absolutely essential for secure remote access, yes. They're commonly referred to as remote desktop connections, or RDCs, when used for remote work sometimes, although that's slightly different technology, but similar concept. VPNs are crucial for secure remote access to company resources. They encrypt data as it travels across insecure public networks. They basically create a private, encrypted pathway, allowing employees to work securely from anywhere as if they were sitting in the office network.
Okay, that covers the networking architecture. Amazing stuff. We've covered the physical components, the hardware, the cables, the network devices, and how they're physically arranged and how they communicate using protocols and layers. But what makes them actually do anything? That's where software comes in, right? It's the instructions. Without it, all that impressive hardware is just, well, a collection of expensive metal and plastic.
Precisely. You can't have one without the other, really. Software is the set of applications, procedures, or programs that provide instructions for a computer to execute. It's the brain of the operation, you can say, telling the hardware what to do, how to process information, and how to interact with a user. The user interacts with a program, which in turn gives instructions to the physical computer's operating system. Software is a vast category. It can refer to programs that manage multiple applications like an operating system itself, or it can be a standalone program like your word processor, or even something localized to a component of a computer or a peripheral device, like the software, the driver, that controls a printer.
So if software is the instructions, what exactly is the operating system then? We use terms like Windows, Mac OS, Linux all the time, but it's often a bit of a black box, just the background that runs everything. Why is it so critical? What does it do?
The operating system, or OS, is truly foundational. You called it the background, and it is, but it's the master conductor of the digital orchestra.
I like that. Conductor.
Yeah, it's the software that orchestrates the global functioning of a group of applications, hardware, and their overall performance. It acts as an intermediary between all these various resources, allowing a user to execute specific tasks without needing to understand the underlying complexity of the hardware. And OS defines the parameters for managing a system's memory, its processes, records, devices, and the user interface you see. By optimizing these critical functions, an OS balances resources and allocates them in a way that allows the entire system to run seamlessly. hopefully without delays or interruptions, even when multiple applications are running simultaneously.
So it manages everything, keeps it all running smoothly.
Ideally, yes. Which is why if an OS experiences a critical error, like the infamous blue screen of death, it can bring the entire system to a grinding halt. That's why stability and robust design are absolutely paramount for operating systems, especially in enterprise environments where downtime costs money.
Right. And firmware. That sounds less common, but I've definitely heard the term. What's the difference between firmware and regular software? And why do we rarely, if ever, update it on most devices?
Firmware is quite interesting and often misunderstood, yeah. It's a type of software, but it's locally embedded directly into hardware. Its primary purpose is to instruct that specific piece of hardware how to operate at a very low fundamental level.
Like baked into the chip?
Exactly. For example, the firmware on your computer's motherboard or within a microprocessor or even in your printer or smart TV, that initial boot-up code. The key difference from typical software is right there in its nature. Firmware is generally not updated frequently, if at all.
Why not? Security patches.
Well, it's because it's so deeply integrated and critical for the hardware's basic function. Frequent updates could introduce instability. And crucially, if a firmware update goes wrong, it can brick the device, render it completely unusable.
Ouch. Bricked.
Yeah. So firmware updates are usually reserved only for critical bug fixes or maybe major security patches discovered later. It's a higher risk update.
Okay, that makes sense. Treat firmware updates with caution. Moving beyond static devices, mobile technology is absolutely everywhere these days. It's fundamentally changing how we work and live. How does that fit into the broader IT infrastructure discussion? It seems like it would create entirely new challenges for managing everything.
Oh, absolutely. Mobile technology has become indispensable for modern IT infrastructure. And yes, it absolutely introduces new layers of complexity and, frankly, risk. Mobile technology refers to any wireless-enabled device that is connected or has the ability to connect to a private network or the internet. This technology allows users to conduct business and communicate in real time, which is absolutely crucial for business continuity, especially during crises, remote work scenarios, or just when people can't meet in person.
So phones, tablets, laptops on Wi-Fi.
Exactly. Mobile technology combines various forms of hardware laptops, tablets, mobile hotspots, smartphones with mobile applications, and specialized operating systems like iOS or Android, all designed for seamless connectivity to networks. This connectivity is typically achieved through ubiquitous wireless technologies like Wi-Fi, Bluetooth, and of course 4G or 5G cellular technology.
Are mobile devices EUDs or non-EUDs?
Both, actually. It's important to note that mobile devices can be EUDs, like your personal smartphone or a company-issued tablet, providing direct interfaces with a user. But they can also be non-EUDs. Mobile non-EUDs are wireless devices like routers, switches, firewalls, and wireless access points that might use cellular backhaul or manage Wi-Fi. These run on mobile technology, but they don't directly interface with a person. They support the network itself by broadcasting Wi-Fi or managing mobile data traffic.
Okay. And what about the Internet of Things, IoT? That feels related.
It's very related. An interesting extension of mobile technology is the rapid growth of Internet of Things, or IoT, devices. These typically require either Bluetooth or an internet connection, usually Wi-Fi, to access a larger network. Their mobile range for connectivity is usually more limited than traditional mobile tech like phones.
Like smart speakers, smartwatches?
Exactly. IoT devices are becoming ubiquitous, found in everything from artificially intelligent personal assistants like smart speakers, smart watches, Bluetooth earphones, and speakers, to smart home devices that control lighting, electrical equipment, thermostats, and even major appliances like refrigerators and dishwashers now connect to the internet.
My toaster will soon need a firmware update.
Possibly. But from an IT infrastructure perspective, each of these IoT devices is a new node or point of connection. Each one is constantly generating data, potentially, and interacting with the network, requiring management, security, and connectivity within the broader IT infrastructure. This raises fascinating questions about data ownership, privacy, security vulnerabilities, and just how much of our physical world is now generating digital information and relies on this infrastructure.
It really does. Okay, now let's talk about a truly monumental shift in IT infrastructure, cloud computing. It feels like everyone is talking about it, has been for years. But what exactly is it, and why has it become so incredibly prevalent? It seems almost magical to just rent computing power from somewhere else.
It does seem magical sometimes, doesn't it? But it's based on very real, very efficient infrastructure. Cloud computing is fundamentally a computing model that uses shared resources over the internet. So instead of companies owning and maintaining all their IT infrastructure on premises in their own buildings, Cloud customers rent storage space, processing power, proprietary software, or maybe a combination of all three, from remote servers owned and managed by another company, the cloud service provider, or CSP.
So paying someone else to run the computers for you, basically.
In a way, yes, but it's more nuanced. To understand its appeal, let's contrast it with the traditional on-premises model. When a company acquires its own infrastructure, like servers and data centers, it usually has to purchase enough resources to cover its absolute peak usage.
Like for Black Friday sales or end-of-year processing.
Exactly. They have to accommodate those high-volume periods,
Huh.
whether it's a holiday shopping rush or a critical end-of-quarter financial calculation. But what happens during low-volume times? That often costly infrastructure just sits idle, generating no return on investment, but still incurring power and cooling costs.
Wasted resources.
Significant wasted resources. And on top of that, the company is entirely responsible for all maintenance, security, and technical support on its hardware. This requires a large internal IT team with diverse expertise. It's expensive. Cloud computing addresses this directly by offering what we call infrastructure elasticity.
Elasticity, like a rubber band.
Kind of, yeah. Customers rent only as much as they need, often on a minute-to-minute or even second-to-second basis. So processing and storage are rented in increments of computing power used per unit of time, meaning customers pay lower amounts during low-volume periods and larger amounts during high-volume periods. It scales seamlessly up or down as demand changes. This eliminates the problem of idle, costly infrastructure just sitting there.
Pay for what you use, like
Yeah.
electricity.
Exactly like a utility service. Furthermore, a huge benefit for customers is that the provider of the cloud services, the CSP, usually performs all maintenance and technical support on this hardware, patching, updates, physical security. This transfers a significant operational and financial burden from the client organization to the expert CSP.
So companies don't need as many people managing servers.
Often, yes. This model also creates significant efficiencies. Companies with massive computing infrastructures, the CSPs like Amazon, Microsoft, Google, they can lease their excess capacity during off-peak times or use purpose-built infrastructure designed to support multiple customers simultaneously. Economies of scale. This allows cloud computing customers to gain efficiencies by renting from CSPs instead of purchasing or building out costly solutions themselves.
Makes sense. Any other big benefits?
Yeah, a couple more. Additional efficiencies arise when a company's data is in one virtual location, especially if company operations are spread across many physical locations globally. Data processing can be performed far more efficiently from that single virtual location, and the need for distributed IT hardware support may be significantly reduced throughout the company, freeing up internal IT teams to focus on more strategic initiatives, perhaps.
Centralization helps.
And from a risk perspective, redundancy is huge because cloud service providers often offer distributed redundancy among many data centers, often across different geographies. Having cloud data storage dramatically reduces the likelihood that data is lost, whether it's in an attack, a regional disaster like a hurricane, or even just a localized power outage at one site.
Spreading the risk.
Exactly.
Yeah.
It's a very compelling set of benefits, which is why cloud computing has become so pervasive. It solves a lot of problems of the old on-prem model.
Okay, this raises an important question, though. It sounds like there are different levels of cloud. You mentioned renting storage or processing or software. What are the different ways a company can actually do cloud computing in terms of how much they manage versus how much the cloud provider manages? It feels like it must be a spectrum of control and responsibility.
That's a critical distinction, absolutely. And yes, it's often visualized as a spectrum of shared responsibility.
Yeah.
The cloud computing models represent how much control the customer organization retains versus how much management responsibility is transferred to the cloud service provider, the CSP. At one end of the spectrum, you have on-premises. This isn't cloud, obviously, but it's the baseline. Here, the organization has full control and manages everything itself: applications, data, runtime environment, operating systems, firewalls, storage, networking, and the physical data center. They own and operate it all and bear all the responsibility and cost.
Total control, total responsibility.
Right. Moving along the spectrum, the first step into the cloud is usually AES, or Infrastructure as a Service. In an IES model, the CSP provides an entire virtual data center of resources. Organizations can outsource virtual servers, storage, hardware networking services to third-party providers, generally billed on a per-use basis.
So you rent the basic building blocks: servers, storage, network.
Exactly. The customer organization is typically responsible for keeping the operating environment consistently up and running for users, as well as virtually managing the performance of the physical infrastructure. That means installing their own operating systems, their own applications, managing security above the infrastructure level. The CSP, however, is responsible for the physical management of that underlying infrastructure. The hardware, the virtualization layer, the servers, storage, networking components in their data center. The degree of control the organization has over certain functions can still vary widely across CSPs and organizations, even within IaaS.
Okay, so you manage the OS and apps, they manage the hardware. What's next?
The next step is PaaS, or Platform as a Service. Here, the CSP provides proprietary tools or solutions remotely that are used to fulfill a specific business purpose. Often, this is for developing, running, and managing applications without worrying about the infrastructure.
Platform, like a development platform.
Often, yes. In a PaaS model, the tools facilitate the creation of programs and the delivery of services. For example, building an online platform to sell merchandise or advertise products or construct other websites, all of which run on a CSP's hosted infrastructure. The significant difference here is that the CSP becomes responsible for keeping the application's uptime at an acceptable level. They manage all of the back-end infrastructure, the operating systems, the middleware required to run that application platform.
So the customer just focuses on building their app?
Pretty much.
Yeah.
The customer focuses more on developing and deploying their applications, rather than managing the underlying infrastructure, OS patches, etc.
Okay, less control but less management burden. And the last one?
And at the far end of the spectrum, with the least control for the customer and the most management by the CSP, is SaaS, or Software as a Service. In a SaaS model, the CSP provides a complete business application or software that organizations simply use to perform specific functions or processes. Customers generally purchase the service through licensing, often on a subscription basis, monthly or yearly fee.
Like Office 365 or Salesforce or Gmail.
Exactly. Those are perfect examples of SaaS. The CSP offers access to the application via the internet and is fully responsible for recurring upgrades, security enhancements, and all other support functions. You just use it.
So you manage almost nothing except your users and data within the app.
Correct. And a common extension offered in conjunction with SaaS models are BPay, or Business Processes as a Service models. Here, third parties use SaaS software to deliver specific entire business functions, such as outsourced payroll or billing or logistics services. This essentially outsources an entire business process, not just the software.
Wow, okay. So you can rent parts of your IT infrastructure, IaaS, or a platform to build on PaaS, or even entire software applications. And the level of control shifts accordingly. That's a huge strategic decision for any company, figuring out how much to offload versus keep in-house. But how is this cloud actually set up physically? Or maybe logically? Is it all one big shared internet server farm, or are there different ways these cloud environments are deployed in terms of ownership and access?
Good distinction. Yeah, it's not all the same structure. There are 4 common types of cloud computing deployment models, and each dictates how the cloud environment is shared and owned. First, the public cloud. In this model, the cloud infrastructure is owned and managed entirely by a cloud service provider, like AWS, Azure, or Google Cloud. And the services are made available to the general public or various organizations who want to use or purchase them.
So anyone can sign up and use it, like a public utility.
Yeah, pretty much, yeah. Think of it as a massive shared resource pool. This is often the most cost-effective option for many due to the scale. Second, the private cloud. In contrast, a private cloud is created specifically for a single organization. It can be managed either by that organization itself or by a CSP. But the key is it's dedicated. And the cloud infrastructure can physically exist on the organization's premises or off-premises in a CSP's data center, but still dedicated.
So not shared with anyone else.
Correct. The key is that it's dedicated to one entity, offering maximum control, security, and customization, but usually at a significantly higher cost than public cloud.
Makes sense. More expensive for exclusivity.
Third is the hybrid cloud. This model is composed of 2 or more distinct cloud infrastructures, could be public, private, maybe even on-prem, with at least one being a private cloud component. These clouds remain unique entities but have technology in place that facilitates the portability of data and applications between them, moving workloads back and forth.
Best of both worlds, maybe.
That's the idea. It allows organizations to leverage the benefits of both private and public cloud environments. For example, keeping highly sensitive data or legacy systems on a private cloud or on-prem, while using a public cloud for less critical, maybe burstable workloads or development and testing, moving them between environments as needed. It's all about flexibility and optimization.
Okay, hybrid sounds powerful. What's the last one?
And finally, the community cloud. This infrastructure is shared by multiple organizations, but not the general public. It's shared to support a common interest.
Like who?
Well, this might be companies banding together for specific regulatory compliance needs, like in finance or healthcare, or organizations that share a common mission, maybe government agencies, or companies who need to collaborate closely with industry peers. For instance, a group of healthcare providers might use a community cloud specifically designed to ensure all data is handled according to strict IPA regulations, leveraging shared expertise and infrastructure tailored for that purpose.
So shared, but only within a specific group with common needs.
Yeah. Exactly. It's a shared model, but for a very specific, defined community with common requirements, sort of a semi-private shared cloud.
Got it. Public, private, hybrid community, different ways to deploy. So these cloud service providers, the CSPs, they're the companies actually running all this infrastructure for IaaS, PaaS, SaaS in these different deployment models. Who are they, really? And what's their role beyond just owning the hardware? What makes them so good at this? Why not just do it yourself?
Well, cloud service providers, or CSPs, are third parties that specialize in providing these cloud computing services. This includes everything from application delivery and hosting to ongoing monitoring for their customers. A core part of their role, as we mentioned, is performing all maintenance and technical support on the underlying hardware, effectively taking that burden off the client. CSPs typically possess very advanced skills and extensive experience in managing cloud infrastructure and environments. You're talking huge teams of engineers focused solely on this. This allows customers to take advantage of this specialized expertise without having to build it and, crucially, maintain it themselves. The economies of scale are immense.
They can just do it cheaper and better because it's all they do.
Largely, yes. Their business model often involves either using purpose-built infrastructure designed specifically to support their cloud customers, or leveraging their existing large computing infrastructures, maybe from their own primary business, to lease out excess capacity during off-peak times. A common characteristic of CSPs, especially in the public cloud, is that they often serve multiple cloud customers simultaneously, using common resources and technology for all of them. This is what's referred to as a multi-tenant environment, where many customers share the same underlying hardware, though their data and applications are logically separated and secured from each other.
Oh, multi-tenant, like an apartment building versus a single-family home.
That's a great analogy, yeah. And for organizations considering or already using CSPs, it's vital to know that information about CSPs can often be found in those SOC2 reports we discussed earlier.
Bringing it back to SOC2.
Exactly. These reports provide crucial details regarding the CSP's compliance with regulations or industry standards. This can be critical for users who need to understand controls implemented by the service organization, maybe to comply with things like the postal security requirements for healthcare data, or for potential clients looking for compliance with standards issued by the Cloud Security Alliance, like their Cloud Controls Matrix, which is a framework specifically designed for best practices regarding cloud security, data protection, and compliance in a cloud environment. It gives you invaluable transparency into their operations, which is absolutely essential when you're trusting them with your critical data and processes. You need that verification.
Okay. Cloud computing sounds incredibly powerful, efficient, offers so many benefits like elasticity and redundancy, but with all that outsourcing, that shared infrastructure, maybe the multi-tenancy, it also introduces new complexities and definitely new risks, right? How do organizations manage and even anticipate those risks, especially since they're no longer directly managing all the hardware, maybe even the software? It feels like losing control could be risky.
You've hit on one of the most critical aspects of cloud adoption. It's a huge consideration. While the benefits are immense, the risks are very real and need robust management. You can't just blindly trust. This is where frameworks like the COSO Enterprise Risk Management, or ERM, framework become invaluable. COS, that's the Committee of Sponsoring Organizations of the Treadway Commission. They've developed widely recognized guidance and best practices for internal control, enterprise risk management, governance, and fraud deterrence. Their enterprise risk management integrating with strategy and performance framework provides a really comprehensive approach for addressing an organization's risks.
CESOERM. Okay. What does it involve?
The CESO ERM framework categorizes methods for addressing an organization's risk into 5 interconnected components. And these are supported by 20 underlying principles. The 5 components are governance and culture, which sets the tone from the top regarding risk appetite and reinforces oversight. Strategy and objective setting, which is about integrating risk into strategic planning and defining clear objectives. Performance, which involves identifying, assessing, prioritizing risks, and then reporting on their impact. Review and revision, which is about continuously assessing and adapting to changes in the risk landscape or the business. And information, communication, and reporting, which emphasizes transparent information sharing about risks, controls, and performance. The overall purpose of this framework is to provide practical, customizable principles for managing risks associated with business objectives and strategy, making them applicable to organizations of any industry, size, or type. It's quite flexible.
Okay, a structured way to think about risk across the whole organization. But what's fascinating here is, how does this COSO framework specifically apply to cloud computing, where so much is potentially outsourced? It feels like the responsibility might get blurry, or maybe that a company might think, well, the cloud provider handles security now, which sounds dangerous.
That's precisely the challenge,
Mhm.
and the misconception the COSO framework helps address in the cloud context, a very common pitfall. A key principle that COSO emphasizes for cloud computing governance is absolutely critical. Ownership of risk remains with the organization, even when functions are outsourced to a CSP.
Okay, say that again. Ownership of risk stays with the company.
Yes, you cannot delegate risk ownership. You can outsource the function, maybe the server management, but you cannot outsource the ultimate risk associated with that function. The buck stops with the organization using the service.
That's huge. So you're still responsible if the CSP messes up.
Legally, ethically, reputationally, yes, often you are. Proper governance of cloud computing and CSPs may even include establishing a dedicated cloud computing steering committee within the organization to oversee all cloud efforts, ensure consistent strategy, risk management, and oversight. An organization must also deeply understand a CSP's values and culture, recognizing that the CSP effectively becomes an extension of their own organization, representing them in a way.
You need to trust your partners.
Deeply. Critical considerations include, how does using this CSP affect our organization's overall risk profile? Does it increase it, decrease it, change it? How can the CSP's own risks, like major outages, impact our organization's performance? We've seen huge CSP outages take critical systems down for thousands of clients globally.
Right. Headline news sometimes.
Exactly. What specific responsibilities belong to the CSP versus us, the client organization? This needs to be crystal clear in contracts and service level agreements. For example, a CSP may provide firewall or VPN capabilities, but the configuration and ongoing enforcement of those security policies might be left entirely up to the client organization. That's a common area of oversight failure, assuming the provider handles it all.
The shared responsibility model needs careful definition.
Very careful. And fundamentally, how do the CSP's internal controls actually address risk? Does their SOC2 report look good? Are their controls adequate for our needs? Finally, organizations should continuously update and reassess their strategies whenever there are changes. Changes to their cloud needs, changes to the CSPs they utilize, changes in the threat landscape. It's not a one-time setup, it's an ongoing process of monitoring and adaptation.
So it's a living process. How does COSO help structure that evaluation?
Well, the CSO Enterprise Risk Management Framework offers 8 specific components, slightly different from the 5 high-level ones. These are more tactical, that can be applied to help organizations establish ideal configurations for cloud options, tailoring the solution based on the company's own risk appetite and objectives.
Okay, let's run through those 8 quickly. How do they apply to cloud?
Sure. First, internal environment. This serves as the foundation for a company's risk appetite, helping it understand the level at which it wants to outsource technology functions. A low-risk appetite company might stick to private cloud, for example. Second, objective setting. Management must understand how outsourcing technology functions will help it reach or potentially hinder its strategic objectives. Does cloud help us expand globally faster, or does it introduce unacceptable data residency risks? Third, event identification. Management needs to grasp how adopting a CSP could potentially make identifying risk events more complex, maybe less visibility, or ideally easier if the CSP offers good transparency and monitoring tools. If their system goes down, does ours too? How do we know? Fourth, risk assessment. Management should thoroughly understand the risks associated with its chosen cloud strategy. What's the impact to our risk profile? What's the inherent risk versus the residual risk after controls? What's the likelihood of a major CSP outage or a breach? Asking the tough what-ifs questions. Fifth, risk response. Based on the assessment, management must determine its response to each specific cloud risk. Are we going to avoid it? Don't use cloud for this. Reduce it through controls, like encryption. Share it. Transfer via contract SLA. or just accept it if the impact likelihood is low enough.
Avoid, reduce, share, accept. The classic risk responses.
Exactly. Sixth, control activities.
Yeah.
The organization needs to understand how its traditional controls, detective, preventative, automated, manual, entity-level controls are modified, affected, or even replaced in a cloud environment. Physical access controls are gone. Logical access becomes even more critical. Seventh, information and communication. Management should analyze how operating in the cloud will affect the timeliness, availability, and effective dissemination of critical information, both internally and externally. How will we get breach notifications from our CSP? How quickly? How do we communicate that? And eighth, monitoring. Management must adapt and modify its monitoring mechanisms to properly accommodate the new complexities and distributed nature introduced by adopting a cloud solution. Ensuring controls remain effective over time. This means constantly checking CSP performance metrics, their security reports, audit logs. It's continuous vigilance.
That's a very systematic way to approach it, using that COSO framework. But what are the specific risks that often pop up, the things companies really need to watch out for when they decide to move to the cloud? Can you give us a list of the common pitfalls, the top worries?
Absolutely, and some of these might be surprising. There are multiple risks that should be carefully considered when evaluating CSPs and their services. I'll list out 10 key ones that often come up. 1. Competitor adoption rate. This might sound strange, but it's a strategic risk. If your competitors are rapidly adopting cloud solutions, gaining significant efficiencies in cost or agility, well, a slower organization might fall behind, losing market share or competitive edge. You can't afford to ignore it if everyone else is benefiting.
Interesting. Keeping up with the Joneses digitally.
Sort of, yeah. 2. Being in the same risk ecosystem as the CSP and other tenants. We touched on this with multi-tenancy. In a shared cloud environment, a security breach, or even just a performance issue affecting another customer of your CSP could potentially impact your own operations. You're sharing infrastructure, and their bad practices or a targeted attack on them could have ripple effects on you.
Guilty by association, almost.
Potentially. 3. Transparency issues. The cloud model can sometimes reduce visibility into the CSP's internal operations and controls, making it harder for the client organization to truly oversee certain functions. You're relying heavily on their word, their reports, their audits. Trust but verify is key. 4. Reliability and performance concerns. While CSPs aim for incredibly high availability, often advertising 99.99% uptime, outages or performance degradation can still occur, and a large-scale CSP outage can impact thousands, maybe millions, of clients' critical business processes simultaneously. We've seen it happen.
Yeah, those make the news big time.
5. Lack of application portability. This is often called vendor lock-in. Once an organization builds its systems or stores vast amounts of data within a specific CSP's ecosystem, especially if they use proprietary tools or services unique to that provider, it can be extremely difficult and costly to switch to another provider later. You're effectively locked in.
Hard to move house once you're settled in with custom furniture.
Good analogy. 6. Security and compliance challenges. Ensuring that data remains secure and that all regulatory compliance requirements, think IPAY for health, GDPR for privacy in Europe, PCI DSS for payments, are met when data is processed and stored by the third party in the cloud can be incredibly complex. That shared responsibility model can create dangerous gaps if not clearly understood and managed. 7. Cyber attacks. Cloud environments are massive, centralized repositories of data and processing power. This makes them incredibly attractive targets for cybercriminals. While CSPs invest heavily in security, the shared nature means a single vulnerability or even a simple misconfiguration by one tenant could potentially be exploited across multiple tenants if not managed properly by the CSP or the user.
Bigger target, bigger potential impact.
Exactly. 8. Data leakage. The risk of sensitive information being exposed or accessed by unauthorized parties, whether that's due to a misconfiguration by the client, an insider threat at the CSP, or a successful cyber attack. It's a constant concern that organizations must actively mitigate through encryption, access controls, monitoring. 9. IT organizational change. Moving significantly to the cloud requires significant internal restructuring of IT departments. You need new skill sets, cloud architects, security specialists focused on cloud. Roles and responsibilities change dramatically. Managing this internal transformation, retraining people, hiring new talent can be challenging and costly. It's a cultural shift too.
People need to adapt.
Definitely. And 10, CSP, long-term viability.
Right.
What if your cloud service provider goes out of business or fundamentally changes its service offerings in a way that no longer meets your needs? Or gets acquired by a competitor who might discontinue the service or change terms? Organizations need to consider the long-term stability and strategic direction of their critical partners. You don't want your foundation crumbling.
Wow, that's a comprehensive list of worries.
It is. And a critical insight here, which is often visualized as a kind of gradient of risk. Risk generally increases when moving from a private cloud model, more control dedicated, to a public deployment model, shared, less control. Similarly, risk also tends to increase with less direct control, meaning as you move from an IS model, managing OS, apps, to a PaaS model, managing apps, and further to a SaaS model, managing almost nothing, you are giving up more control to the CSP, and thus potentially taking on more inherent risk if things go wrong with a provider. The less you manage yourself, the more you rely on and are exposed to the risks of your provider. It's a fundamental trade-off: control versus convenience and cost.
That makes perfect sense. More convenience, less control, potentially more risk exposure to the provider's issues. So with all these inherent risks and that clear gradient of control and exposure, how do companies actually decide which cloud option to go with? It must be a really complex decision matrix, weighing costs against security needs, compliance mandates, performance requirements. It sounds almost like a high-stakes gamble sometimes.
It absolutely is a complex strategic decision, not one to be taken lightly. Organizations evaluating various cloud options must choose among public, private, or hybrid models, and they need to understand that their computing environment may be combined with other tenants, particularly in public or community cloud settings. Companies really should aim to understand the behavior and profile of those other tenants if possible, because their activity, maybe they get hit by a massive denial of service attack, can have a direct impact on your own IT operations sharing that infrastructure.
Your noisy neighbors can cause problems.
Effectively, yes. The enterprise risk management composition, the risk profile of two companies sharing the same cloud infrastructure, will be combined or overlap to differing degrees depending on the model selected and the isolation provided. Implementation is another key factor in the decision. Some cloud applications, like simple SaaS solutions, can be quickly adopted by an organization with minimal investment. They're ready to use, whereas others require substantial time and expense to implement. Think about migrating complex legacy systems, maybe decades old, to an IaaS environment. That can involve completely re-architecting applications. It's a massive project.
Lift and shift versus complete rebuild.
Exactly. Management must evaluate this effort and cost prior to committing to a specific cloud solution or migration strategy. They also need to determine whether they fully understand any compliance risks that come with having a CSP assume certain functions. When some functions are shared or supported by a cloud application, it can sometimes remove transparency and oversight that might have otherwise existed in a company before the cloud solution was adopted, which can be a compliance nightmare if not carefully managed and documented.
So visibility can decrease.
It can, if you're not careful. Let me give you a real-world example to illustrate these points. The case of Fingard Financial. Imagine them. They're a global market infrastructure operator, and they're considering outsourcing their clearing and settlement functions to support real-time stock trades for their clients.
Okay, that sounds absolutely mission critical. High volume, needs to be instant, super reliable, super secure.
Exactly. Failure is not an option. Their CFO presented senior management with 3 distinct options from different providers, each with very different risk and cost profiles. Option with a core was the Mistral Clearinghouse platform. This company utilized a public cloud model, housing clients with up to 50 other companies per computing machine. 50.
Wow, 50 companies sharing one machine. That sounds crowded.
Very crowded. Their pricing was based on the relative use of the platform with a monthly minimum. So if Fingard made more trades than another institution sharing the same machine, Fingard would pay more. The significant risk here, obviously, was the high number of shared tenants in that multi-tenant public environment. Fingard was extremely concerned about the platform crashing during a stock trading frenzy, a market panic or surge, which could prevent investors from making trades, magnify losses, or cause them to miss out on huge gains.
Catastrophic potential.
Absolutely. This represented a high-risk, shared public cloud scenario. Cost was lower, but the risk of performance impact and shared vulnerabilities was significant.
Okay, option 1. Cheap but risky public cloud.
What was option 2? Option 2 was Cliff Clearinghouse Partners. This firm offered a completely custom-built clearinghouse platform. It would not share physical space or computing power with any other entity.
A dedicated private setup.
Essentially, a private cloud managed by the CSP, yes, dedicated just for Fingard. This dedicated option was, naturally, the most expensive, coming in at a hefty 5% of trading fees paid by investors.
5%, that's huge.
It is. However, it was also presented as the most secure option. with the most advanced computing power on the market. And importantly, it included backup platforms at a separate geographical location for redundancy in case the primary platform failed. Disaster recovery built in. This represented a dedicated private cloud solution managed by a CSP, offering maximum control and lowest risk for FinGuard, but at a serious premium.
Option 2, very expensive, but maximum security and dedication. What was the middle ground?
Option 3 was the R&M Group Clearinghouse. This organization offered shared cloud hosting, but with a maximum of only 2 other companies on the same machine and location, not 50.
Okay, much less crowded than option 1.
Significantly, pricing was on demand, based on the level of computing power used by FinGuard, at a fixed rate per hour, with advanced computing power having a higher price than general-purpose power. This represented a shared cloud, but with significantly reduced risk compared to Misrock due to the very limited number of shared tenants. It was a middle ground option, balancing cost and risk better than Misrock, but still with some shared environment exposure, unlike Cliff.
So 3 clear choices. Cheap, risky, expensive, secure, mid-price, mid-risk. What did FinGuard choose?
Given FinGuard's global operations and the absolutely mission-critical nature of real-time stock trading, they ultimately decided to go with option 2, Cliff Clearinghouse Partners, despite it being by far the most expensive.
They paid the premium for security.
They did. Their reasoning was clear. They wanted a dedicated, highly secure, and fully redundant platform because they operate globally and are responsible for vast amounts of financial transactions that directly impact their clients' wealth. Reputational risk was paramount. They were willing to pay that premium for minimal risk in such a critical function. Option I, with its large number of shared tenants, was deemed far too risky for their core business operations. It's a perfect example of how an organization's risk appetite, its compliance needs, and the sheer criticality of the function being outsourced drive the cloud adoption decision, often prioritizing security and dedication over mere cost savings when the stakes are high enough.
That makes total sense. You get what you pay for, especially with risk. So if we connect this back to the bigger picture, it sounds like organizations can't just outsource and forget it. They need active, sophisticated strategies to manage these cloud risks continually. What are the best ways for organizations to respond to these myriad cloud risks once they've made the leap? What are the recommended actions?
Absolutely. Active and ongoing risk management is paramount. You can't set it and forget it. Given the variety of cloud computing options and the risks we've discussed, management must adapt its programs and controls so that each risk related to their specific cloud environment has the appropriate response. It's a continuous process. First and foremost, policies need to be implemented, reviewed, and enforced. Policies to reduce the likelihood of unauthorized cloud activity, sometimes called shadow IT. This is particularly important for data security and compliance issues, making robust data classification processes and policies an absolute necessity. Organizations must know exactly what data they have, where it is stored, including in which cloud services, and what its sensitivity level is, so they can apply the right protections, whether it's unclassified public info or highly sensitive personal data requiring encryption and strict access controls.
Know your data, classify your data.
Foundational. Then, to determine whether those safeguards are in place and working correctly, there should be periodic assessments of the CSP's control environment. This means regularly reviewing their SOC 2 reports, maybe conducting your own audits if permitted, ensuring the CSP is upholding its end of the security bargain, that their controls are operating as described, and that they meet the agreed-upon service level agreements, SLAs. There also needs to be strong internal management oversight, specifically designing the way in which controls are monitored, even when outsourced, to maintain accountability. Who is responsible internally for checking the CSP's performance and security?
Assigning ownership internally.
Yes. And when incidents, such as a cyber attack or a major outage, do occur, and they will, a comprehensive, well-rehearsed incident management plan should be in place to control and mitigate the threat effectively and quickly. This plan should cover both the organization's responsibilities and how it will coordinate with the CSP during an incident, ensuring clear communication channels, defined roles, escalation procedures. It's about preparedness for when, not if, something goes wrong.
Practice makes perfect for incident response.
Definitely. Now, risks related to vendor lock-in are common, but maybe not always evident in companies with long-standing vendor relationships. They get comfortable. Therefore, developing robust CSP exit strategies is actually crucial, even if you don't plan to leave soon. This gives the organization a contingency plan. Should an abrupt switch be required due to issues like unacceptable performance, massive price hikes, or the CSP's long-term viability coming into question, It ensures business continuity and the ability to migrate data and applications to an alternative provider if necessary, reducing dependence on a single vendor and giving you leverage.
Always have a plan B, especially for critical systems.
Always. Finally, monitoring the regulatory environment for changes is also critical to minimize the risk of noncompliance. This is huge. Countries across the globe are rapidly implementing protective rules to restrict the use of sensitive information outside of their borders, data residency laws, making it imperative for companies operating in multiple nations to be constantly alert to data residency and privacy regulations like GDPR, CCPA, and others.
The rules keep changing.
Constantly. Additionally, if a company is publicly traded, non-compliance disclosures may be required by regulators like the SEC if CSPs are supporting critical business processes. So transparency and compliance monitoring are not just good practice, but often a legal necessity. You have to stay on top of it.
Wow. We have truly gone on a deep dive today. That was incredible. From the microchips inside your computer to the vast invisible networks connecting the world, the OSI model, and then right into the strategic, often high-stakes decisions companies make when embracing the cloud and how they manage the risks. It really provides a foundational understanding for navigating our modern digital landscape.
Indeed. We've seen how essential it is to understand all these interconnected layers, from the physical hardware and the instructions of software, to the intricate dance of network topologies and that multi-layered OSI model that makes it all work together. And we've explored all the way up to managing the complex risks of cloud adoption using sophisticated frameworks like COSO, emphasizing that even when you outsource, you absolutely retain ownership of your risk. The real takeaway, I think, is that modern IT infrastructure is less about just physical boxes in a room now, and more about an intelligent, dynamic, interconnected ecosystem, spanning on-prem, multiple clouds, the edge. It's complex.
So what does this all mean for you, our listener? Well, the next time you use an app, stream a video, interact with a company online, or even just send a simple email, you'll have a new and hopefully profound appreciation for the incredibly sophisticated, resilient IT infrastructure and cloud computing models working tirelessly behind the scenes. It's truly a marvel of engineering, logistics, and organization, making the digital world function as seamlessly as it usually does.
And for you, our learner, maybe consider this provocative thought as we wrap up. As technology continues to evolve at this breakneck speed, how will our increasing reliance on global, distributed IT infrastructures, especially the cloud, how will that continue to reshape not just businesses, but also our fundamental understanding of concepts like data ownership, personal privacy, and maybe even national security? In an increasingly interconnected and sometimes fragmented world, where does the data live? Who controls it?
Something to definitely ponder as you navigate your own digital world and think about where your data is going and who's managing it. Thanks for diving deep with us today.